I'm delighted to see so many people here today. I think this is a record turnout indicating the great interest in energy topics right now and the urgency of addressing the climate problem. I'm Denise Maswell. I'm a professor joint between C-PREE and the Woodrow School and Civil Environmental Engineering. And I'm delighted to welcome Professor Jesse Jenkins here as our first speaker for this semester. Jesse just joined Princeton this fall as an assistant professor with a joint appointment in the Department of Mechanical and Aerospace Engineering in the Andlinger Center for Energy and Environment. And we're delighted to have him. I'm sure all of you are also delighted that he's here. He's an energy systems engineer with a focus on the rapidly evolving electricity sector, including the transition to zero carbon resources, the proliferation of distributed energy resources, and the role of electricity in economy-wide decarbonization. His research focuses on improving and applying optimization-based energy system models to evaluate low-carbon energy technologies, policy options, and robust decisions under deep uncertainty. He's published extensively on energy systems analysis and also has a very modern form of communication and outreach, Twitter, with over 25,000 followers at this point.
They were all here.
He completed
Half of you are in the room.
and struggling to get in. He completed a PhD in energy systems and a Master's of Science and Technology Policy at the Massachusetts Institute of Technology and a Bachelor's in Computer and Information Science at the University of Oregon. Prior to Princeton, he was a postdoctoral environmental fellow at the Harvard Kennedy School and the Harvard University Center for the Environment, a researcher at the MIT Energy Initiative, and the director of Energy and Climate Policy at the Breakthrough Institute, and a policy and research associate at Renewable Northwest. We all look forward to his talk, Getting to Zero, an American Transition to a Net Zero Energy Emissions System.
Thank you, Denise. It's a pleasure to be here, and I'm floored to see so many people here. It's really exciting to see a full room, and also exciting because you're going to get to see a sneak peek at some of the findings from the Princeton Net Zero America study, or project, which a number of us in the room have been taking part in for the last many months, and we're excited to sort of be transitioning from our initial phase into phase of starting to share preliminary results and then really drilling down into what it takes to build a net zero greenhouse gas emissions economy for the United States. So we're going to talk about that, and we're going to focus specifically on the role of the electricity sector, which is where my research primarily focuses. And as we'll see from the presentation, is really, I argue, one of, if not the central linchpin to any strategy to deeply decarbonize the economy and confront the challenges posed by global climate change. So I'm going to start by talking about why zero, why net zero, which is the focus of the talk. Why do we have to get emissions all the way down to net zero greenhouse gas emissions, which means that for every ton of greenhouse gases that are caused by human activity, there's at least 1 ton of human-caused sequestration of emissions that would, negative emissions that would offset any remaining human-caused emissions. So we can either drop total emissions to zero, or we can have some amount of residual emissions and offset those by capturing CO2 and sequestering it in ways that draws down carbon dioxide or other greenhouse gases in the atmosphere. So when I started talking about net zero, which was, I guess, maybe 2016, we started to focus really in on this question of what it takes to get all the way down to zero emissions and not just say 80% or 60% reductions in CO2 emissions. It was really, I thought, an academic topic. I had to argue to people why we should focus on zero emissions and not more immediate goals like, say, 50% reductions by 2030 or 2040. And since I've been doing this research just in the last couple of years, this is no longer a purely academic topic. 3 states in the country and many countries globally have now legislative requirements on the books to commit their state to reduce emissions to net zero greenhouse gases across the overall economy. That's New York, Hawaii, and Nevada. And 3 states have recently enacted executive orders from their governors to do the same: Massachusetts, California, and Montana. And I would expect this map to populate quite a lot further over the next 12 to 24 months. So this is no longer just simply a rhetorical question or an academic question. These states have laws on the books or executive orders in effect that target their state policy towards achieving this goal of net zero greenhouse gases, or you might also hear it termed as carbon neutrality. In Congress, there's been significant effort on the part of House Democrats as well to introduce legislation that would outline both the overall goal and a set of sector-specific measures to drive the economy towards net zero greenhouse gases. So back in November of last year, 150 co-sponsors in the House supported introduction of a bill that set the broad goal of net zero emissions or 100% clean energy economy-wide by 2050. And then Frank Pallone is the chair of the House Energy and Commerce Committee here from New Jersey here, and other leaders from the Energy and Commerce Committee released not yet a bill, but a comprehensive sort of outline of legislation that they plan to put forward and have put forward after a number of hearings with experts over the last year to talk about what will be required sector by sector to get to that goal. If you've been following the Democratic primary, you'll know that actually every single one of the Democratic primary candidates have committed to a goal of net zero greenhouse gases by 2050 at the latest. I didn't show Yang on this picture because he's missing, but he one-upped everybody and targeted 2049 just to get one more year ahead of everybody. But basically all of the candidates have supported the goal of net zero emissions economy-wide by 2050, with more specifics on a sector-by-sector basis. Okay? So this is really part of the public policy discourse in the United States as well as other countries. France, the UK, Sweden, Finland have all committed with legislation to net zero goals as well. So it's not just a US phenomenon. And that means that the kind of research that we're doing on this question here at Princeton all of a sudden becomes extremely relevant. Because I'd argue that basically no one has any idea how to do this. We know that it's necessary. We know some of the tools that are required, but it's time to drill in and figure out how we're going to get to net zero greenhouse gas emissions. So where did all this interest come from and why now? I would argue that most of it traces back to the IPCC, the Intergovernmental Panel on Climate Change's recent special report on what it would take to hold global warming, average global warming to 1.5 degrees Celsius above pre-industrial levels. So this is a special report that came out in October 2018, and it generated a lot of news coverage. I think in ways that previous IPCC reports have not done quite to this scale. It broke through a lot of the mainstream news, generated a lot of discussion, at least among those communities that are concerned about climate change and their constituents and politicians that are paying attention to those constituencies. So that report, we're already at about closing in on 1 degree Celsius of average warming over pre-industrial levels. So that additional half a degree is really a tight goal. And it's the aspirational goal that the global community committed to at the Paris Accord on climate change. They said that they wanted to hold global warming to no more than 2 degrees Celsius, and if possible, to cut emissions down to 1.5 degrees, to hold warming to 1.5 degrees. So what does that take? And here's where the net zero goal comes in. This is the global pathway for CO2 emissions, and I've cut off the other greenhouse gases. They don't quite go to zero, and therefore the pathway for greenhouse gas emissions is to get to zero if we're targeting 1.5 degrees Celsius sometime roughly between 2045 and 2060. Global emissions of greenhouse gases from human-caused activities have to be in balance with human-caused sinks of net negative emissions that we are also causing. And if we are targeting the less stringent goal of 2 degrees Celsius, but still ambitious, that means global emissions of CO2 have to be at net zero sometime between 2060 and 2080. Now, they also don't just go to zero, they then go net negative, because to reach net zero greenhouse gas emissions in total, we have to actually take CO2 emissions to a negative level to offset or counteract the remaining emissions from methane that comes from rice cultivation or livestock and other things that we're not going to be able to eliminate to zero most likely, and nitrous oxides that are also greenhouse gases largely from agricultural activities. So the assumption in these studies is that we can't get those down all the way to zero, and therefore to get global greenhouse gas balances to zero, we have to take carbon dioxide to a negative level sometime in the second half of the century. That's just the math of the balance. How do we get from, basically we're still seeing global emissions rising at a slow pace. We haven't even turned the corner yet, let alone see these kinds of rapid declines in emissions globally. I'd like to point out, too, that these are sort of arbitrary numbers, of course, 1.5 and 2. They're sort of nice round numbers in Celsius. They're not quite so round in Fahrenheit. And of course, they're arbitrary. There isn't a hard cutoff in the scientific literature at either of those values. But what we do know is that every 1/10 of a degree of warming matters, and that as that warming increases, certain thresholds and certain damages do exacerbate into certain Earth systems and human systems that are important to us. So this graphic from the same IPCC special report shows sort of roughly, notionally, the gradients as damages increase in certain types of activities. whether they're ecosystems that might be important to us, like warm water corals or mangrove forests, or they're human-caused impacts like crop yields, or human system impacts like crop yields and heat-related mortality and morbidity from heat stroke and other related issues. And you'll see that there's a gradient. There might be some nonlinearities in these systems and individual feedbacks, but the overall system, there aren't any hard thresholds at 1.5 or 2 degrees. What we do know is that cooler is better and warmer is worse, and every 1/10 of a degree matters. And to get to any of these goals, whether it's 1.5 or 2, we have to get to net zero greenhouse gases as soon as possible. That's really the thing to take away. Drive emissions to zero as soon as possible. And it's the what's possible part that's going to determine what kind of warming we see in the end. This is a nominal statement, a normative statement from me, not a scientific statement, but I would argue that the United States has both the moral responsibility and the means to lead in this transition. So if this is the average for the global transition to reach net zero greenhouse gas emissions sometime between 2045 and 2080, the United States should be ahead of the curve. We have the wealth and the technological capabilities to lead, and arguably we have a moral responsibility given that the United States is the single largest contributor cumulatively to global greenhouse gas emissions in the atmosphere. So we're no longer the largest single emitter, we're number 2 behind China, but we have been the largest historical contributor to the warming that is on pace right now due to historical emissions. And so we have arguably the means and the obligation, I think, to lead in that transition. So what is it going to take then to decarbonize the United States? Well, that's the focus of our Net Zero America project here at Princeton, which has been ongoing for quite some time. The PIs are Eric Larson and Chris Gregg, who are here in the front, and myself. And we have an enormous and excellent team of researchers, both faculty and postdocs here at Princeton, many of whom are here in the room as well. Aaron Mayfield, Andrew Pascali, Xuan Zhang, all here. Raise your hands. Been doing a ton of work on this. And we have a number of consultants and other supporters from outside of the Princeton community that have helped add expertise to this study. So this is a big effort, and it's been supported by the Climate Mitigation Initiative, BP, and the Andlinger Center and ExxonMobil, Dow, and the Princeton Endowment as well. So it's a big effort, and we're excited to preview a sneak peek of what we found from our modeling results that take a look at economy-wide what it's going to take to decarbonize each of the sectors of the United States. So I just wanted to put this slide up here, which comes from Ryan Jones, who's one of the modelers at Evolved Energy Research that's supporting our work, which shows that why we need to be thinking about 2050 and planning ahead right now and not, say, in 2030 or 2040. This shows the sort of notionally the average number of stock replacements of certain types of infrastructure or capital investments, durable goods, that are going to roll over between now and 2050 for different types of technologies. So a complex fluorescent light bulb might last for 3 to 10 years. I think that's assuming 5 maybe here. So we have a number of times we're going to replace lighting in buildings, right, or fluorescent bulbs in commercial spaces. An appliance like a refrigerator or a washing machine might last for 10 years. So we're going to have maybe 3 of those before 2050. But for important things like air conditioning systems and furnaces, HVAC systems, vehicle lifetime, it takes about 15 years for the average vehicle to retire. Commercial boilers in buildings might last 20 or 30 years. And things like power plants and pipelines, we basically have 1 stock turnover between now and 2030. So a power plant or a pipeline built in 2020 will almost certainly still be operating, or at least could continue operating economically and reliably in 2050. So from the perspective of energy infrastructure and the investments that businesses and governments and agencies are making right now, 2050 is the day after tomorrow. It is not 30 years from now. It is not a long way off. And so that means that we have to know where we're going. This is an imperative for policymakers, I would argue, to give that clear direction to industry and to households and businesses so they can plan those investments in light of where we're going. But it's also something that we as academics need to be thinking very carefully about, not just the next 10 years, but the next 30, and the kinds of decisions that have to be made now so that when we make these investment decisions, they're invested in ways that are consistent with a net zero greenhouse gas emissions world, and not something that we're going to have to then go and rip out in the future. Because when you make one of these investments, the incremental cost of buying, say, an electric vehicle instead of an internal combustion engine vehicle is relatively small. But if you have to retire prematurely a power plant after 10 years of operation, or a pipeline after 10 years of operation, those sunk costs add tremendously to the overall cost of transition. So this is an affordable transition path, we'll see, only if we sort of hit the timing right. If we don't, then it's going to make it much more costly or more likely that we'll delay. So this is why we have to focus on these questions right now and not some far future date. Okay, and this is what concerns me, is that if we kind of only focus on the near term and don't think about the timing ahead and don't have the policy environment in place now, not just in 2050, we'll run into dead ends. We'll proceed down a certain path, we'll do the easy stuff, and we'll find ourselves locked in because we won't have planned for the sort of nonlinear increases in challenges that go along each path, or we'll have made investments that have long-lived implications that weren't well considered at the time and make it much more challenging, generate lock-in that prevents us from moving easier to a low-carbon path in the future. All right, so let's size up the overall challenge of getting our economy to net zero greenhouse gases. So these are starting to see, we'll see modeling results from the net zero study. This is our reference case, which basically builds out the kind of business as usual projections from the US Energy Information Administration about how end use demands for electricity or energy services are going to grow over time. So this assumes certain things about the increase in vehicle miles traveled, for example, as the population grows and as commute patterns change, or the increase in the square footage of building space that needs to be lit or space conditioned for heating and cooling. Okay, so those end use demands. And then the reference case just assumes kind of business as usual, policy as usual trajectory. And this is what we see. You get a little bit of an improvement in oil consumption in this time frame, which is basically the current fuel economy rules. And then they kind of tap out because they're not continuing to go further. And then population and GDP growth pick back up, and we see this sort of increase. So it's roughly flat overall in terms of our current energy consumption. And if we look at it, we basically see about a third of it, or 23 quadrillion BTUs, is a quad, just a big amount of energy. We consume, as you can see here, about 65 quads in total. So a quad is a substantial share, over 1% of final energy consumption. And so basically a third of that is electricity, hydrogen, steam, and biofuels, which we can essentially decarbonize directly, right? We have zero carbon ways to make electricity, hydrogen, and steam. We can use wind, solar, nuclear, carbon capture and sequestration, et cetera. So we have sort of drop-in replacements for these end uses that are carbon-free. But that still leaves 46 quadrillion BTUs, or 2/3 of our total energy consumption in the reference case, that are from hydrocarbons, either gaseous fuels, so natural gas primarily, pipeline gas, or diesel, jet fuel, gasoline, et cetera, a little bit of coal, but primarily it's petroleum and then natural gas, right? And these are important sources of end-use consumption for transportation, for heating, for industrial processes, et cetera. And we don't have an easy way to take drop-in replacements for these today available that are carbon-free. So our options then, if we want to sort of eliminate these, are basically four. We can improve our energy productivity, so we can reduce the total amount of consumption needed to fuel the same amount of economic activity or end-use energy demands. That can be thought of as traditional kind of efficiency policies, but also just improvements in the productivity of industrial activities, which is something that is ongoing on a regular basis. Globally, we have about a 1% improvement per year in the amount of the amount of GDP we support per unit of energy across the global economy. And largely in the places like the US, we're seeing this continued improvement because more and more of our economic activity is coming from less energy intensive activities like services compared to high intensity activities like manufacturing or agriculture. So that all kind of rolls up in here. We could also shift modes, so we could go from on-road freight to rail freight, which is more efficient or productive. And we could just conserve. We could use less energy services when they're not necessary. So all those help us kind of knock this down. But it's not going to take it to zero, right? There's a limit to how far we can go with that. We can electrify more of these end uses. So this is the share in business as usual, but as we'll see, we can increase that share significantly, and then we can channel those carbon-free electricity sources to power those other end-use activities. And we can do two things to zero out the remaining hydrocarbon fuel demand. We can create drop-in zero-carbon fuels, hydrogen, or upgrading hydrogen and CO2 through Fischer-Tropsch processes into synthetic gasoline or diesel or jet fuel that it comes from carbon-free sources. Or we can continue to use some amount of fossil fuels, and then we have to offset the emissions from that combustion. So we then have to do negative emissions through either direct air capture, or we use chemical means to pull carbon dioxide out of the air and sequester that, reducing emissions in total, or through biomass with carbon capture and sequestration, BECCS, where we use biomass, which is through its growth activities is pulling carbon out of the atmosphere and fixing it in the form of the biomass substance. And then we're going to convert that into some format where we can capture the CO2, make use of the energy or hydrogen, and then sequester that CO2 for a net offset or a net negative process. So those are basically our 4 strategies. And that's what our model is looking at when we try to decarbonize this. Is let's say, how do we get from this to something that's 0 emissions employing these strategies, okay, this set of strategies. And that leads me to think about basically 6 pillars of overall decarbonization, that 6 core components of the strategy that hold up the sort of frame of the overall net zero plan. The first, as I mentioned, is energy productivity improvements. Okay, we want to get more with less energy. The second is to electrify more end uses. So the more we can rely on zero carbon electricity instead of hydrocarbons, the easier it's going to be. So electric vehicles or heat pumps instead of furnaces in buildings, or electric boilers for industrial heat processes instead of natural gas. How much can we expand clean electricity? So the electrification strategy only really works if it's driven by carbon-free electricity. If we keep using coal and gas, it's not going to help. Can we develop net zero carbon fuels? So this is either zero carbon processes or the continued fossil use with offsets from negative processes. We got to capture a lot of remaining carbon emissions, either to create the net zero kind of context, or to allow us to continue to use large point sources of fossil fuels like natural gas to produce hydrogen, capture the CO2 and sequester it, or large natural gas-fired power plants that could capture the CO2. So anywhere we have a large point source that could still use fossil fuels, we could maybe capture that CO2 and sequester it, and that might be a cost-effective way to keep using fossil fuels as part of the overall solution. And then finally, a big piece, which I won't talk much more about now, is we have to enhance the land sinks. So the natural biomes that are absorbing and fixing CO2 through natural processes, if left unattended, are likely to degrade. Our business as usual trajectory is that the sort of natural land sink in the United States for carbon dioxide is going to decline by about half unless we take proactive action. And if we take proactive action, which our report will get into the number of steps that aren't necessary there, we might actually be able to expand that land sink significantly. And in our study, that effectively offsets not quite all, but nearly all of the non-CO2 greenhouse gas emissions in the economy that we can't eliminate. So it's kind of fitting. We have agricultural related, sort of processes that produce methane and nitrous oxides. By enhancing our land sinks and our stewardship of forests and other ecosystems, wetlands, et cetera, we can offset most of that residual emissions, not quite all of it. And so I think our strategies are about, 170 million metric tons of negative CO2 emissions to get the remaining non-CO2 greenhouse gases offset. So the rest of it, the big bulk of the non-CO2 greenhouse gases are handled by enhancing and protecting our land sinks. All right, so that's a big piece of the overall picture as well, which not my expertise, so I'm going to leave it there. Okay, so I'm going to talk for most of the rest of this about the electricity sector. All right, that's where I spend most of my time thinking about. And it wasn't an accident I sort of picked this as an area of study because I do think it plays an outsized role. It's not the only thing we need, as you'll see, but it plays an outsized role in the overall effort to confront climate change. And that's because we basically have two big challenges, right? We have to drive emissions down to zero from electricity production. And as you'll see, we need to dramatically expand the role that electricity plays in the overall economy so that we can push down the amount of hydrocarbons we still have to decarbonize through other generally more difficult or costly means. So let's talk about the role of energy productivity and electrification in making the overall size of the challenge a bit more manageable first. So this was our reference case. And we ran 2 different scenarios we created with different degrees of electrification of end uses, both of which include a large amount of end use productivity improvements or efficiency improvements as well. So we're assuming that industrial processes get more productive every year, that lighting and heat pumps and vehicles get more productive every year. And we're going to try to electrify a good chunk of the remaining end-use demands. And so what that leads to, both the combination of end-use productivity improvements and the fact that electric motors and heat pumps are more efficient than combustion and internal combustion engines at converting primary to final energy, we get a big improvement in the total amount of final energy demand overall. And so that falls by 20 to 30% across the 2 scenarios. Where the big difference between these 2 is how much additional gain we get from the productivity improvement from electrifying certain activities. So An internal combustion engine delivers very little of the total energy in the tank to the wheels of the car compared to an electric motor and electric drivetrain. And so that fuel shifting also gives us a productivity or efficiency improvement as well. Then, because we're not only getting that productivity improvement, but also substituting electricity here, this is the big growth in electricity in this wedge, for end-use activities, we're pushing down the remaining hydrocarbon energy demands from 2/3 in the reference case to only about 20 to 35% or so in the remainder. So we're down by 40 to 67% from the base case or the reference case to somewhere between 15 and, say, call it 15 to 30 quads of energy. Okay? So that makes it much more manageable to deploy the other strategies that I talked about, drop-in fuels, netting out continued fossil use, et cetera, to get rid of this remainder. If we didn't knock down the total size of the hydrocarbon demand, we run out of available low-cost options, basically. As you'll see, we're going to use up all the biomass. We're going to have to start doing expensive things like direct air capture if we don't knock this down a lot. All right, so that's the first challenge. This is what it sort of looks like for the different scenarios we constructed in terms of the pace of electrification. This is the light-duty vehicle market, and up here, cars and trucks, and then medium-duty trucks and heavy-duty trucks. And in our rapid electrification or high electrification case, we're at 50% of all new vehicle sales. This is sales, not stock. So it takes a while for the sales to get, once the sales get to 50 or 100%, it then takes a while for the stock to turn over. And so if we want to have the stock be 100% carbon-free by 2050, we need to be turning over sales much faster than that. So this is another one of those ways where planning ahead is really important. So in the rapid case, we reach 50% of new sales of cars are electric by 2028, so just 8 years from now, which is maybe 2 model design years for automakers from now, 1 or 2. And then for light-duty trucks and heavy, all the trucks basically, they get to 50% either electric, which is the yellow, or electric or fuel cell, which is hydrogen fuel cell, which is this color for the heavy and medium, by 2033 as well. So very quick pace of turnover. And we have similar aggressive assumptions in the high electrification case about how fast heat pumps penetrate into the residential and commercial space heating and cooling market and take over from boilers, gas or oil boilers. In the delayed electrification case, we sort of push all that back by a decade roughly. And that means that we don't hit 50% of new car sales until 2038 and the heavy and light duty trucks until 2043, which maybe is a more kind of business as usual or modest trajectory for the increase in EV sales. And then by 2050, what that means is that basically by 2045, we get to 100% of new car sales and trucks are either electric or fuel cells, so electric drivetrains run by fuel cells and clean hydrogen, by 2045 in all these cases, and pretty close, 90% or so, by 2040. And in the delayed electrification case, it kind of maxes out around 80 to 90% by 2050 of sales, and a much lower share of the overall fleet. Okay, so this is kind of the range that we're playing with. And you'll see that this has a really big impact on the rest of the puzzle. So how much we can push electrification really drives how much we need biomass, how much we need to make zero carbon fuels from electricity, and how much offsetting we have to do in the overall rest of the economy. So what was surprising is I kind of assumed that in the delayed electrification case, we would be using less electricity overall, right? Makes sense. We're not using electricity for cars and heat pumps and space heating, et cetera, so we'll probably use less in total. But what I was surprised to find from these results, which makes sense when you start to unpack it, is actually delaying end-use electrification increases total electricity production. Okay? So the only substitute for electrification is more electricity, which is kind of important. And that's because we shift from the final energy demands running on electricity, which is more efficient, to continuing to use internal combustion engines and boilers and things like that, running on zero carbon drop-in fuels that are produced upstream by electricity, by a combination of electrolysis, which is this here, so using electricity to split water into hydrogen, and then using that hydrogen either directly or combining it with CO2 to make drop-in fuels. And then we have a big chunk of electric boilers in industrial processes where it's relatively cost-effective to install a dual fuel system where you use electricity through a boiler, electric boiler when electricity is free and you have lots of wind and solar available, and you switch back to natural gas when you don't. And so that's a way to sort of directly use electricity in lieu of natural gas in certain industrial processes where you need heat and steam. And then finally, this last piece in the low biomass case, so this is our low and high biomass, and then our high and constrained electrification cases. We do a lot of direct air capture as well, because we've used up all the biomass in these two cases already before we get to this sort of marginal need for additional electricity or additional fuels due to the delayed electrification. And so the only way to do some of that is to actually take hydrogen and add it to carbon dioxide from the atmosphere to make synthetic long-chain hydrocarbons, to make jet fuel, make LPG gas, make synthetic methane for pipeline gas, or to just offset the continued use of fossil gas. Okay, so those are your two options. And both of those require some additional netting if you've already maxed out your biomass. We don't see the additional direct air capture in the high biomass case because there's some slack in that system where you don't use all the biomass in this case, and you do in this case. So we're increasing the total amount of biomass as a way to help deal with it. But even then, the electricity demand goes up by a slight amount. So even with more biomass available, we have to rely on electricity upstream for boilers and for hydrogen production. So there's really no way around this challenge of dramatically expanding the role of the electricity sector in our economy. The question is simply whether we make rapid progress on end-use electrification, which is ultimately going to be lower cost and and higher efficiency, or whether we have to do it on the upstream side of the equation. So that's what leads to this sort of twin challenge for the electricity sector, which is that we need to drive emissions down to zero emissions from power generation, and do so while basically doubling or more total electricity production in the US over the next 30 years. So this graphic shows our current electricity mix in the bars. So the red here is natural gas, the black is coal, which together provide about 60% of our electricity today. The remaining 40% on top here is from existing zero carbon sources. So between nuclear, which is about 20%, and then the combination of wind, solar, and hydro, a little bit of biomass and geothermal, we get another 20% from those. So we're about 40% carbon-free today. So we're not starting from zero, luckily. But we still have 60% of our energy from fossil in the electricity sector. Then the bars over time show in the kind of unconstrained case, I only showed one case here, the decline in the current stock. So the phase out of coal, which goes away entirely by 2030, the most cost-effective immediate thing we can do is shut down coal plants and replace them with a combination of wind, solar, and natural gas in places that we haven't completed that transition yet. And then we also have to start shrinking the natural gas role, at least when it's without CO2 emissions or blending with hydrogen. So we're declining our role for natural gas. And so I assume here we keep half of the existing nuclear fleet online through to 80 years life, which is twice as long as they're originally licensed to operate, but seems to be feasible. So we say roughly half of that fleet is going to stick around in the main cases. And then let's assume we keep or repower all of the existing wind, solar, and hydro. You know, maybe we'll have to replace some of the wind turbines, but we'll keep them online. Then the lines here are the total electricity demand over the scenarios. In the blue is the high electrification scenario, and the yellow is the low. And then the solid lines are our high biomass, and the dotted line is our low biomass availability. And so you can sort of see the difference that each of those scenarios has. But in general, even, the range it's significant, but we're talking about at least doubling across all of those scenarios by 2050. So if we just take the difference between the line and the bars, we get the total new carbon-free electricity that we have to bring online each decade. All right, so the new stuff. And that's what this line looks like. So it's the same color coding. So we start out at zero because we've got our 40% or 20% from 40%, sorry, from carbon-free sources. Then we need to ramp that up. So let's kind of give some context to this. I don't know what a terawatt hour is. I have a hard time getting any sense for the scale of these magnitudes, right? So this is total 2020 zero carbon electricity generation superimposed. All right, it's about 1,600 terawatt hours. So what this is saying is that sometime between now and 2027 to 2028, depending on the scenario, we have to double all of the existing carbon-free generation that we have in the US today. So all of the wind, all the solar, all the hydro, and all the nuclear. We have to build all of that again from new carbon-free sources in the next less than 10 years. Then this is all US electricity generation from all sources as of now, about 4,000 terawatt hours. And sometime, depending on the electrification path, between 2037 and 2042, we need to build the entirety of the US electricity grid worth of generation from carbon-free sources. It took us 150 years to build the last grid. And we have to do all of that again over the next 20 years, call it. All right? So this is an enormous undertaking. I will not sugarcoat this. I mean, this is, as you'll see, requires unprecedented scale-up rates for most of the technologies we're talking about. And again, is why we have to start planning for this transition now and establishing the policy environment that can help this kinds of massive change and rapid investment move forward without significant uncertainty and delay. If we compare this to the annual rate of additions, we can sort of take these terawatt hours, and if we divide by the number of hours in the year, we get the average generation or power capacity, power output, so the rate of production that we would need from carbon-free sources. So take the terawatt hours, divide by 8,760 hours in the year, and you get the average gigawatts of new capacity that we need to bring online. I say this in average gigawatt terms because depending on the technology you deploy, they're used at different rates of utilization. So a wind farm that produces maybe 100 megawatts at its maximum obviously doesn't sustain its maximum output all the time. On average, it might be producing, say, 40% of that maximum. So we call that the capacity factor, or you can just think of it as the average utilization rate of a particular technology. And so if you multiply the total capacity or maximum nameplate capacity of a technology, its highest rated output, times its average utilization rate, you get its average gigawatts of power production, so the average rate of power it could produce at. A nuclear power plant that's about 1,100 megawatts, which is the size of the AP1000 nuclear plants that Westinghouse was trying to build in South Carolina and Georgia. They failed in South Carolina and are still trying to finish the ones in Georgia. Those are about 1,100 megawatts each, and they produce about about one average gigawatt of electricity production in the year. So you can think of an average gigawatt, which is the units here, as one big old nuclear plant, or enough to power about 1 million US household electricity needs for a whole year. All right, so we use just a little bit over a kilowatt per household on average. And so one average gigawatt is roughly 1 million houses, maybe 875,000. So good sized city worth of electricity. And what we need to do, if we divide the sort of average pace across the decades, is bring online somewhere between 28 and 37 average gigawatts of new clean electricity every year for the next 30 years. Now put that in context, the average build-out rate from 2010 to 2018 of all of the wind and solar and biomass that we've built in the US averaged to 3.4, so say 3.5 average gigawatts. And the peak single year was 5.3. So we need to be going somewhere between 5 and 7 times faster than the peak total wind and solar year that we have on record, which was 2016. Looks like 2020 we're going to set that record again, and it's going to be a little higher than this, which is good, so we're making progress. If you look at the fastest sustained rate at which the US has brought on zero carbon generation, and you think about scaling to population size, since this is in the past and we have a lot more people and resources now, the average sustained rate at which we brought new nuclear for the peak decade, so the sustained decade-long rate, which was from 1981 to 1990, was 7.4 average gigawatts, so roughly 8 big nuclear power plants every year on average for that time period. And remember, we need to get that rate up to somewhere around 30. So this is not business as usual. We have not done this before, at least with clean sources. If we look globally for other precedents, at least we can see some things that are on the right order of magnitude, which is good. So this is, again, the range. The darker bar is the high electrification, and the lighter bar is the low electrification range for each of the, the high biomass and low biomass availability for the two electrification cases. If we look at Germany, which has been a global leader in bringing online renewables, and we scale based on population size. So Germany is a much smaller population than the US, so let's scale their additions per capita to equivalent to the United States. If we were bringing online renewables as fast as Germany has, we would have averaged 6 average gigawatts over a decade and had a peak of about 12. So they're doing about twice as fast as we are on per capita terms. But even that is only a third of what we need to be doing to get here. US natural gas boom, build out in the 2000s when we deregulated our electricity markets, is the fastest on record in the US for sustained build out of new electricity generation. The peak was 60 nameplate gigawatts in a single year, which was huge. So that's even more than we need. But the sustained rate over the decade was about 23 average gigawatts, maybe 40 nameplate gigawatts, because of the capacity factor. So we actually built a ton of natural gas-fired power plants in a decade. And so that gets us, roughly on the same magnitude at least. And then if we look at the fastest rates at which carbon-free generation is brought online by any country over a decade-long time period, it's the nuclear build-outs in France and Sweden in the 1980s, late 70s to 80s, where in per capita terms, again, if we scale it to the size of the United States population, we had between 26 and 30 average gigawatts of nuclear a year, sustained for a decade, which is really fast. And that's driven Sweden and France's electricity emissions rates down to some of the lowest in the world, basically the lowest. They're, I think, about below 50 grams per kilowatt hour, which is a tenth of the United States average in France, and even lower than that in Sweden because of their use of hydro as well. So I look at this and I say, well, at least we have a couple examples in both kind of capitalist, free market type environments here, and in state-led utility, owned by the state government or national government type environments here, of at least roughly the pace of build-out that we need, sustained over a decade. So what I sort of take away from this is at least a little bit of hope. This is a little bit scary, but at least these give us a little bit of hope that if the right policy environment is in place, or the right investment environment is in place, that you can see sustained investment and build-out on the scale that we're talking about, but only under those conditions. If you don't have the right market conditions and policy conditions in place, we're not going to see this kind of sustained rate. You see some booms and busts. Some years are high, some years are low. The market follows trends, and we're not going to be anywhere near the pace that we need here. And so this is where, for the policy school, the folks who think about the policy side of this, and where our report sort of leaves off, we kind of give you the scale of the challenge. It's trying to think about what is the policy environment that needs to be in place in different economies, different contexts, to get to the scale of deployment that we're talking about and to sustain it not for a year, not for 10 years, but for 30 years. All right, so I'm going to talk about some of the building blocks now of the clean electricity sector. And I'll start with renewables, because in almost all of the scenarios that we're running now, renewables really take the center stage. So wind power crossed about 9% of US electricity generation last year, which now puts it on scale with all hydropower production in the US. Right, so it's pretty big. I mean, particularly at a regionally relevant scale, we have certain states and markets that are approaching 20 or 30% of their electricity from wind, similar to how we have regions that are largely powered by hydropower at sort of 30 to 60% scale. So nationally, it's closing in on 10%, and regionally, it's a very significant resource for some parts of the country. Solar at utility scale crossed the 1% mark a couple years ago, doubled again in just another couple years, and is sort of on a few years. It's basically a decade behind where wind is at in terms of its growth, and so maybe we'll be on a similar scale soon. But what we see in these scenarios, and that's because, before I get to the scenarios, that's because, we'll go with some good news here, the cost of wind and solar, as well as lithium-ion batteries, which I show here on this axis, have plummeted over the last decade. So the wind costs have come down, but the average cost of generating electricity from wind at a good wind site in the country has fallen by about 70% just over a decade. And for solar, it's fallen basically 90%, and similar order of magnitude for lithium-ion battery packs. Which are used both in electric vehicles, which is key, and in stationary batteries for electricity storage. So I used to work as a renewable energy advocate from 2006 to 2008 in Oregon, where we helped pass the Renewable Energy Act in Oregon, which set up the Renewable Portfolio Standard. It's a policy that requires 25% of the electricity that the large utilities in that state generate had to come from renewable sources by 2025. It was since doubled to 50% by 2030. And when we were talking about that way back off the edge of this map, that's how old I am, the chart was way up here. We didn't even talk about utility solar. It was unbelievably expensive. It was not something we even contemplated being part of the picture in the near term, at least. And wind, if you could get a wind farm for under $100 per megawatt hour with the federal subsidies, that was a steal. Now, if you look across the country, wind and solar are basically converged in price. They're both under 5 cents a kilowatt hour or $50 a megawatt hour. And in most parts of the country, they're probably the cheapest way you can generate electricity, even from any new technology, right? It's cheaper to keep running an old gas plant or an old nuclear plant. But if you want to build something new, these are often the cheapest technologies available. And that's why we're seeing huge investment from the private sector. So I used to think this was sort of job done, right? We would sort of get the cost down, and then the private sector would take over. And we've gotten maybe half the job done, but I'll talk about why this isn't sort of the slam dunk that I thought it was back then. So here's the, we'll just take two of the scenarios to simplify. Here's the high electrification, low biomass, and the low electrification, high biomass cases. And you see that in both cases, solar here and onshore wind, and then this is a little bit of offshore wind here, are the dominant sources of our total electricity generation by 2050. They're basically 75, 80%, 75% say of our total electricity in these scenarios. Right, so they have moved from alternative energy sources to mainstays of our energy system. They're on the, in terms of energy shares, they have exceeded the total combined share that we get today from natural gas and coal, which again, remember, is about 60%. So here they're more than 60%, and we've doubled the total pie. So this is a huge role for wind and solar to play in our energy future. They're sort of the centerpiece overall. In most of these scenarios, we have some where we constrain these. But getting there requires, as we alluded to before, a rapid increase in the pace at which we're deploying wind and solar. Right? Because if you want to have them be dominant in the system, they not only have to deploy as fast as fossil fuels, they have to deploy faster to keep up with the growing demand. And basically, we're going from, so this is the projected build over here in 2020 from the EIA, based on all the plants that have sort of announced their planned construction. We're going to set a new record. These are in total nameplate capacity terms, not average gigawatts, because we're comparing like and like. And we're basically going to build 18.5 gigawatts of wind and 15.2 gigawatts of solar this year. That's what the projection is. And you can see that's actually about on pace with the first 5-year increment. These are 5-year periods, 2020 to 2025, and then each 5-year period to 2050. So we're kind of on pace with the first 5 years of the plan at that pace, if we can sustain it. But then you see all these scenarios ramp up fast. In the high biomass case, it kind of peters out at about 100 gigawatts in total wind and solar addition a year for a 5-year period or 10-year period. But in the other cases, it rises up to between 150 and 200 gigawatts of total deployment over at least a 5-year period, which exceeds even the fastest build out of wind and solar in China, which is the global record for annual additions of wind and solar to date, which is about 54 gigawatts of solar and 30 gigawatts of wind in different years. So 80 gigawatts in total. We're exceeding that pace by the 2030s in all of these scenarios. So we have to be mustering the kind of policy and investment environment to be building at a world record pace wind and solar and sustain or accelerate those paces to get to this scale role. Right? So this is by no means smooth sailing. And a big focus of our study is to try to think about what it actually takes. This is the model results, okay? Again, it just spits out these numbers. That's nice. All the math adds up. But the big challenge, and this is where most of the work in the study is going to be coming from Princeton, is how do we actually do that? Where does this stuff get built? How do we site it? Who wants it in their backyard? How do we create the sort of siting regime so this doesn't conflict with other land use or conservation priorities? Right? All of these sorts of challenges that are not all in the model. We can kind of constrain the model and push it one way or another to kind of represent those, but these are non-modeled factors. Right? The model just spits out a nice clean trajectory, which is great. You can see the scale of and magnitude, but actually translating this into reality is a huge undertaking, and that's where a lot of the policy thinking, a lot of the detailed analysis has to come going forward. We did run some cases where we said, well, what if we can't deploy renewables that fast? We cap it at the record pace that we've seen so far, and we kind of limit it to that each year, and that's this case here. And then we also ran some cases where what if we don't want to deal with fossil fuels anymore, and we don't want nuclear in our economy, we just want to have a 100% renewable powered economy, right? And that's the pace that you need here in these two scenarios, depending on the amount of biomass availability. So here, this isn't just 100% renewable electricity, but also economy-wide. We're not going to use any fossil fuels or nuclear throughout the economy. Whereas in these other scenarios, we do have some remaining fossil fuel use. It's less than today. And we do have some remaining nuclear use, mostly less than today, except for this constrained scenario. And you just see that, even where here we were talking about world record pace sustained for 3 decades, here we have to just go right off the map, right? And we just, we have the physical infrastructure to do this. Like we could build that much stuff probably in the US. But this is just, it's a whole nother order of magnitude, or at least 3x larger pace of change. Okay. So just remember, this is the world record China totals here, and then we're talking about going 3 times faster than that for solar and 3 to 4 times faster than that for wind every year by the end of the pace. All right, so renewables are big. They're going to be important. We may fall at the end of the day somewhere between our renewables constrained case, which we clearly can do. We've already sort of done that. It's the kind of historical rate. And somewhere between here or even faster if we can get on this pace. But even then, in all these scenarios, the electricity capacity that we've installed is not all renewable. Even in the 100% renewable electricity case, we're still burning something. We're burning hydrogen in those cases or synthetic natural gas. And so we have, here is total US electricity capacity, so power generating capacity in the US, which is just over a terawatt of capacity. And you can see that this is wind and solar, which again are huge, but then, and some storage, some batteries here. But all this other stuff is what I call firm capacity. So these are technologies that are available any time of the year, for any length of time, for however long you need them. You can rely on them to be firm, to generate power when you need them. And all these scenarios have almost as much firm capacity as we do in the base case, or today, right? So even in a 100% renewable scenario, we have a big slug of reliable, always available type generators. Why is that? That's sort of weird, right? So the wind and solar are the cheapest way we can generate electricity, and yet we still have these expensive things around, like gas with CCS, or we're going to make synthetic hydrogen and then burn it at several times more expensive than the cost of natural gas today. So this poses a riddle, which was nicely summed up by one of the members of the California Independent System Operator in an article I read a couple weeks ago. He's the former president and CEO of Patagonia as well. And he made this statement that in California today, even, not just in 2050, but today, it could actually be more expensive to add cheap solar to your grid than to add expensive geothermal. Right? Sort of like a Cohen or a Riddle, right? Like, how can it be more expensive to add something cheap than something expensive? Well, let's walk through a quick example of this, and I'll try to leave a little time for questions at the end of this because I know I'm running a little late. We'll actually play this out. So we have gas. We can use gas until we can strain it out of our system. And that costs, this is the average cost of electricity from these sources. So wind and solar are here. They're the cheapest way we can make electricity today. This is about what things cost today. And here's gas at a little over 5 cents a kilowatt hour. And let's say we have an expensive, clean, firm option that's more expensive than everything else. We're going to use demand and wind and solar profiles from New England, because I put this together when I was at MIT, so we used New England numbers. This is the hourly demand in the ISO New England, the New England regional grid, for every hour of the year. That's kind of annoying to look at, so let's shift it around to what's called a load duration curve. So all I did is reorder this from chronological order to highest to lowest hour of the year. Okay, so this was that high hour in August, or September 8th at 5 p.m., and this is the lowest hour of demand throughout the year. And I'm going to make the model, this is a simple spreadsheet model, not the one we use for our research, but I'm going to make it increase the amount of energy we get from clean sources in 20 percentage point increments. So I'm going to start by saying you have to get 20% of your energy from something clean. It could be wind or solar. You pick the model. And then I have dials here that show what happens to the value of additional wind and solar as we deploy it. So the first thing is the energy value. This is the substitution of megawatt hours of energy from wind and solar for something else, say natural gas in this example. And a value of 100% means that every megawatt hour I produce from wind or solar, the grid can use it and it can displace a megawatt hour of natural gas and save all the fuel cost and variable wear and tear associated with running that natural gas plant for that hour. So 100% means we use all of it and every megawatt hour displaces gas. Then we have what's called the capacity value, which is that for every 100 megawatts of peak capacity or nameplate capacity that I add from wind or solar, how many megawatts of natural gas can I shut down entirely? So how much firm capacity can I get rid of? And what we see is that it already starts out very low. That even at this 20% share, wind on average during the time when we need the most firm capacity, which is September 8th at 5 p.m., is only generating 9% of its maximum. So for every 100 megawatts of wind I add, I can only knock off 9 megawatts of natural gas. And for solar, it's only 4% because it's 5 p.m., and maybe it's a cloudy thunderstorm day in New England, and so there's not much solar. Okay? So I can add a lot of capacity, but I'm not going to be able to shut down much of the natural gas. So even though we get 20% of our energy here, we've only reduced the need for firm capacity from 34 gigawatts before to 33. So we've knocked down 1 gigawatt of firm capacity despite getting 20% of our energy from solar. All right, and then the last dial is overgeneration. So this is the amount of the wind and solar that we generate that has to either be wasted because we can't use it, or it has to be stored, or we have to develop some flexible source of demand that can suck it up when it's available, like hydrogen electrolysis. And that's at 0 right now, but as you'll see, it starts to grow non-linearly. All right, so let's add some more to the mix. So now we're going to go up to 40%, and the first interesting thing happens, which starts to give us some intuition about our riddle, about why adding something cheap can make things more expensive. That is that even though the solar was the cheaper of the two renewable resources we had, when we go to 40%, it does increase the solar, but it starts to add more expensive wind to the mix too. And the reason for that is that the energy share, the energy value of solar falls faster than the energy value of wind. And that's because the output of solar is more concentrated, right? You get this big peak of output in the middle of the day, whereas the wind kind of undulates along on a more random long-term signal. And what that means is that there's some periods here now when we are over-generating electricity, enough to supply 3% of our total demand if we could take this blue wedge and move it over here. And what this is saying is that 23% of all the solar production that we would add from the next megawatt of solar that was added to the grid occurs in these hours here when we already have too much clean energy. Right? And so the wind and solar at that hour are just displacing some other amount of wind and solar that would be curtailed. And that wind and solar has no fuel, and so there's no fuel saving value. So the value falls rapidly. The wind is more spread out, so only 9% of the next megawatts worth of production would occur in this hour. And so it retains its value better. And that means that even though it's more expensive, it has higher capacity value and higher energy value. And so you want to add some of it to the grid along with the cheaper solar. So we have to pay attention not just to the cost of the technology, but also to the value that it brings and how it changes over time.
So could that be shifted by using batteries?
Yep. Yeah, so this is a simple example where we don't have any batteries, and we don't have any way to use that over generation by increasing our consumption. And in our models, it both happen. And we can use some of that, and that helps slow but not eliminate the decline in the value of the energy saving value. And that helps the wind and solar shares go higher. But those technologies aren't free either. You've got to pay for the battery. You've got to pay for the electrolysis. And so the balance is where, that's what our models do for us, is they find the overall economic balance of these technologies. So this is just a simpler example. Then when we go to 60%, interestingly, the share of solar grows quite a bit. And that's because the share of wind grows quite a bit. And that's because the solar energy keeps falling. And we've moved our net peak, or the time when we need the most firm capacity, actually from September to a different night, August 19th, even later in the day, when it's less windy. So the capacity value of wind and solar ultimately goes basically to 0. You can add as much as you want, and it's not going to let you shut down your gas plants. So you don't save the capital, you just save the fuel. And that's why we describe them as fuel-saving resources. When you go to 80, it gets non-linearly harder. So now we're generating enough that we would have to store, we could take 20% of our annual energy demand if we could take all this blue stuff and store it and use it over here. And that has some cost. All right? And then if we say, all right, before I didn't let the model pick any of the clean, firm technology because it was just too expensive, so forget it. We took it off the table. But if we let the model pick, at that level, it actually picks about 15% of the energy from that expensive clean, firm technology. It could be nuclear or geothermal in California, something way more expensive. So this is sort of the answer to the riddle, which is that even though it's more expensive, it has 100% capacity value. Every megawatt of something firm I add, I can knock off a megawatt of natural gas. And it has a very high fuel saving value because I can concentrate my production in the most valuable time periods when I'm using natural gas still, and lower it in the areas when I'm not, which you can't do with wind and solar, right? They produce when they produce. So it retains its value much more so than the variable renewables. And that's why an optimal mix of technologies that's lowest cost as a system includes a bunch of different technologies, some of which are more expensive than others. And that's why I liken comparing the cost of a wind farm or a solar farm to a nuclear plant or a gas plant as like comparing the cost of a banana to a burger. Right? It's good to know bananas are cheaper than burgers, I think. But you're not only going to eat bananas just because they're cheaper, and your doctor's certainly going to yell at you if you only eat burgers. Right? No, that wouldn't be very healthy. You need a balanced diet. Right? You want different nutrients in different combinations, and what you eat, that sort of certain things you eat determine how valuable the other things are. Right? If you're getting a lot of potassium already from bananas, forget about it. You don't need it from something else. So this is a cheeky example, but it's a way to just say these are not direct substitutes. Right? First, a banana is not a substitute for a burger. It's a partial substitute. Right? They both give you calories, but they're not really direct substitutes. And just like a balanced diet, what you eat determines the value of the other stuff. Right? So it's the diet as a whole that is important,
not the nutrients in an individual piece of food. And the same is true for our energy system, and that's why we have to run these complex models to try to understand the interactions, because they're nonlinear, they're often complex, and they're not immediately intuitive. And that's why you have to think beyond sort of simple metrics like just comparing cost. Okay? All right, so I want to sum this up by just saying wind and solar can be stars. They're going to be, I think, in my personal projection, but it's just my view. This is our star point guard from the women's Princeton team, I believe. Was doing quite well this year, I've heard. I haven't followed it really, but they're going to be stars, but you're not going to win a championship if you just have a star point guard, right? You're not going to win even if you have a couple of star players. You might win individual games, but you're probably not going to win the season, right? In order to put together a championship team, you have to have all the right star players in all the right positions on the court. And that's what we have to do to sort of build out our energy system at the least cost. Wind and solar and batteries are going to play key roles. They're going to be star players in certain positions, but they have a particular role in the overall mix, and we have to complete the team. And this is where I think I'll leave it due to time, but the rest of the team, right? So we have wind and solar up here, which I describe as fuel-saving technologies, because as we saw in the last example, when we have them, we displace the fuel consumption of something more expensive like gas. And then what I call fast burst technologies or balancing resources, which is where demand flexibility and response and battery storage play a role, where you can take some of that over generation and move it some other time period, and you can provide quick bursts of flexibility that have a lot of value. But these technologies are not good for sustained output, right? You might defer when you're going to charge your electric vehicle for a few hours, as long as you have enough in the tank to go to work the next morning. But you're not going to stop consuming electricity in your car for 3 weeks because it wasn't very windy or very sunny for those 3 weeks, right? And the same with batteries. You can use a lithium-ion battery, very cost-effectively for a few hours to move energy from, say, 1 p.m. to 6 p.m. when that peak happens. But you're not going to move it from March to July, right? It just doesn't really work economically. And so what we need are this ring of technologies down here, the firm low-carbon technologies, which unfortunately are not scaling or as mature as wind, solar, and batteries, right? They're not as cost-effective. They're not scaling as rapidly as we're deploying the other technologies now. And so this is where a lot of the work has to happen over the next decade to make sure we complete the team. We get the rest of our star players. And I'm agnostic as to which of these technologies pans out. And we really don't know today, I don't anyway, which is the most likely to succeed. And that's why we really need to be working on all of them, I argue, to make sure we can improve the suite of technologies that we have and complete the low-carbon team so that we can fill the critical role of carbon-free electricity in the overall system. So if you've got large reservoir hydro, like Quebec or Sweden, great, use it. That can play that role, but most places don't. If we wanted to have long-duration electrochemical or thermal or chemical storage, it's possible to do that, but on the scales and with the utilization rates that we're seeing, you need to see orders of magnitude cost reductions relative to batteries. So you need to see something on the order of $1 to $10 per kilowatt hour of storage cost versus about $200 to $300 for batteries today. So this is a very different path than lithium-ion batteries. Hydrogen storage underground maybe, large compressed air storage, and maybe there's a few that can make that role, and I've got a paper coming out on that soon. And then the other ones are all generation sources: geothermal, nuclear, gas or coal with CCS, biomass, or net zero gases. So either zero carbon gas itself, hydrogen, or synthetic methane, or we use some blend of hydrogen and remaining natural gas, and then we offset the residual emissions from that with direct air capture or biomass with CCS, which is one of the things our model picks up a lot. So this is our set of options. None of those is ready for prime time today, I would argue. They're not. Nuclear costs a ton. New designs are still in licensing. CCS is still at a demonstration type scale. We built a couple power plants, none for natural gas at scale in the US. And we're really still need to push on the ability to burn high blends of hydrogen in turbines. Okay, we're limited today. So these are sort of our options. All of them have challenges. And if we don't focus the next decade on completing the team, then the sorts of scenarios that we look at in our modeling are not going to pan out, or at least are not going to be cost effective. So I'll leave it there for time. Got a couple more slides, but that's all right. Thank you.
Well, thank you for that super illuminating talk. We're a bit over.
Yeah, I'm sorry I filibustered, but
if anyone wants to leave, please
yeah.
go ahead now. I think we'll stick around for another 5 minutes for a
Yeah, I'm
couple
happy to stay.
additional questions. And Jesse's around, so I'm sure you can track him down someplace to ask any further questions that you might have.
Thanks. Any questions? In the back? Yeah.
I'm wondering what role crowdsourcing might play in terms of rooftop solar versus local battery storage.
Yep. Yeah, so the question was about the role of distributed resources like rooftop solar or battery storage in meeting these sorts of needs. That's actually was the topic of my dissertation, interestingly, at MIT, was sort of looking at this trade-off between large and small-scale versions of the same technology. So the interesting thing about batteries and solar PV is that they're both based on the same small modular technology, right? A panel, a 300-watt, solar panel or a 10-watt cell, a little, battery cell, but they can be assembled at everywhere from kilowatt or watt to multi-megawatt scale. And even though they can be readily distributed, there are still significant economies of scale involved, such that bigger utility scale solar projects, at least in the US, cost about half as much as a megawatt scale distributed solar project, and about a third to a quarter what a rooftop solar project costs in Massachusetts. So it might be $3 to $4 a watt to put solar on your roof right now in Massachusetts, in New Hampshire, sorry, where are we? New Jersey. It would cost about $1 a watt to build a utility scale solar for the same technology. In Europe, that's not quite true. There's a lot of costs that are quite lower for distributed, such that it's only about a 50 to 100% premium for distributed solar in Germany or Australia or other markets. So we could get that cost gap down. But there's going to be a cost, an incremental cost of going smaller, and that should argue for building bigger, all else equal. On the other hand, you can get more value out of a distributed technology because it can be located closer to consumers where they need energy, and therefore you can avoid a lot of the costs related to networks. Now those costs are not infinite, and so the challenge really is to find locations where the incremental locational value, on the one hand, exceeds the incremental cost of smaller scale systems. And then within that location to build the largest, cheapest system that can capture that locational value, which is often not on a rooftop at your house. It's probably more like what the solar system that Princeton has across the way, which is at the multi-megawatt scale. It's still distributed, it's still close to the substation, it still provides all those benefits, but at a fraction of the cost of the same number of solar panels distributed across roofs. So that trade-off is really important from a societal perspective. And I'd argue that our policy environment is not well designed to kind of let people figure out that trade-off. We put our thumbs on the scale in a lot of different ways across the value chain. Yeah.
What about concentrated solar, operating a steam engine, Rankine cycle, with heat storage in terms of molten salt?
Yep. Yeah, so it's a possibility. We have a couple plants out in California and Nevada that do that. At the current cost that we see and we put into our models, it's basically dominated by a combination of solar PV and lithium-ion batteries because the costs have come down so much further and are projected to continue to do so, and they provide a similar service. And so unless we sort of see an accelerated learning for solar thermal and thermal storage, it's unlikely to catch up to the cost reductions that we've seen due to scale for solar PV and storage. So if you'd asked me that question in 2009, I would have been a lot more bullish on solar thermal because we were building a few large multi-hundred megawatt scale projects and they could have come down that cost curve, but solar PV has just raced away. And so in the market now, we're seeing very little investment in that versus PV and batteries, and that's what our modeling shows as well. So unless you sort of see a step change, you can accelerate. They provide basically the same service as PV and batteries, but at a higher cost at the moment. Yeah.
Thank you very much for a packed, power-driven talk. My question has to do with something that just got a kind of whisper past, namely coal.
Yeah.
Last week in the New York Times, they indicated that in Fujiyama in Japan, they're going to put in a big coal-fired plant. And that was going to be the first of 22 coal-fired plants. Well, how much do you know about this, and what are the possibilities of turning around that idea?
Yeah, so Germany just opened a brand new state-of-the-art coal plant this year as well. What's the common thread between those two examples? Yeah, they're getting rid of their nuclear fleets, both of them. I mean, Japan's keeping some of them around. Roughly half of the nuclear fleet in Germany has been shut down, and the other half's going away in the next few years. And basically, both countries after Fukushima, the Fukushima nuclear disaster, decided that it was too high risk, for different reasons, I would argue, but there was too high risk to continue operating their nuclear fleet. And so for at least the next couple decades or decade, they put nuclear retirements higher in priority than fossil retirements and climate change. That's a value judgment. I have a different calculus that I would have chosen for myself, but they're democratic societies and they pick their priorities. But it's very clear that when you elevate nuclear retirements over fossil retirements, you slow things down at best and you go backwards at worst. And I think that's a relevant point to make for other audiences that we're making this decision here in New Jersey to keep our nuclear power plants around, except for Oyster Creek, but for the next few decades as a foundation upon which to build additional wind and solar and shut down gas faster. That's the fastest way to make progress on CO2 emissions. Shut down coal first, then oil if you got it, then gas. And then when that's done, you can retire your nuclear fleet if you want from a climate perspective. If you have other priorities, then you shift the order around and the climate challenge suffers. The progress on climate suffers. Yeah.
I wanted to ask about your model includes obviously, we've already said that we haven't reached peak emissions worldwide.
Yep.
Have you guys taken into account some of the accelerating emissions negative feedback loops between forest fires and
Yeah, so the question is about the kind of feedback loops in the climate system that accelerate over time as we warm. The wildfires in Australia or the western United States this year, which have been devastating, release a lot of CO2 emissions. Yeah, so I guess we started from this goal of net zero by 2050, which is sort of generally informed by the IPCC targets, although arguably it's not consistent with a 1.5 degrees Celsius path unless we have a lot of negative emissions in the future. It's an overshoot path if it is. Because as you saw, the sort of global trajectory was net zero sometime around 2050 globally. So the US probably has to get there faster. But this is hard enough, I think. When we see in our scenarios, it's quite daunting challenge to get to net zero in the US by 2050. And so we picked that as the kind of goal. And as I said, really, every tenth of a degree matters, partly because of these feedbacks that occur. And the faster we get to zero, the better. And so if we can find a way to accelerate this, great. But we started with the 2050 goal because it's consistent with a 1.5 to 2 degree range and depends on what happens after 2050. The world doesn't stop at the end of our models. But it's not, I wouldn't say it's the most aggressive 1.5 scenario or bust. We're trying to map out comprehensively what it would take to get to zero out emissions in the US, and 2050 was a pretty aggressive initial time frame to look at.
So Person Eric mentioning that in your model you assume, so there's going to be Riddle for wind and solar, you assume that it's going to be the same kind of conditions as today. To what extent do you think that would reduce the feasibility of the scenario, for instance, wind and solar potential?
Yeah, good question. Yeah, so climate change is going to potentially affect the potential output of wind and solar as well. So the question is, we didn't really factor that in our modeling because we're using historical weather data to project the production of wind and solar in the future. That's a great question. It's been on my mind a bit lately. I've seen a couple studies, particularly for wind, in the mid-latitudes of the northern hemisphere. On some warming scenarios, there's a potential for average wind speeds to drop, which would obviously impact the productivity of the wind in the US. The paper I read, which I've only seen one or two papers like this, it was mostly the big drops were in the RCP 8.5 scenarios, so the very accelerated warming type scenarios, which hopefully we seem to be off trajectory, at least on the social side of that, the human cause side. If we get a bad feedback or the climate sensitivity's higher than we thought, we might be on a similar warming trajectory. But hopefully we're more in a 3.5 degree world rather than a 6 degree world at this point. But that, and hopefully we can bend that down further. So the scenario that was a RCP 4.5 or 4 scenario in that paper was less dramatic. I think the bigger issue is probably dealing with interannual variability, which can go up and down by 20% from year to year for wind in certain large regions, which we don't capture really in this modeling right now. This is an average typical kind of year. But there's probably some additional redundancy in the system that you need that we're not picking up here to get through the wind drought or the solar drought year when it's just a bad 6 months. And that has happened. I saw there's some stats for the American West, the whole Western Interconnect. Wind production was down like 20% for the first 6 months of the year in 2016 relative to the previous year. So there is a bit of variation. And it's sort of like a hydro-dominated system where you're dependent on rainfall and snowmelt. They have to have some redundancies to get through the bad years. And we may have to think about that more as well if we're more, if we're 70% reliant. And that increases the value of these firm options because some of them, like hydrogen combustion, it's low capital cost, very high fuel cost. So it's fine to build a lot of turbines and not use them very often, and then keep some of them around for the bad years. You got to figure out how to pay those plants for the years they're not operating, but that's one way to do it.
Well, we have our work cut out for us.
Yes, we do. And
Jenkins
welcome
again.
all your contributions to working on this if that's the field you're in. So, thank you.